Welcome to the second Solfem v3 tutorial. In this tutorial we will cover how to create mesh consisting of beam elements from scratch, and then applying section properties, creating a solution, applying boundary conditions, loads, everything. We will also create the solve file and run it through the solver before opening the results to have a look. So, let's start by opening up a terminal window and navigate to the folder where we have the Solfem v3 code and to the subdirectory work directory. From here we start up the Python script program.py, and we want to use the viewer, so we select the viewer. Now I'm going to extend this terminal window a bit because we will want to see the messages that are written in the terminal window as we work, and make this a little bit bigger, easier to see. So the program is started, and let's begin by making our mesh. First we have to create a new mesh, so just an empty mesh. Okay, and we can start by putting some nodes into our mesh. So let's start with one at at these coordinates 0, 0, 2, so x, y, z, and if we click this button, nodes will become visible, so that's useful when we are building from scratch. So let's add some more nodes. How about it doesn't really matter at this point, we will just modify if we are not satisfied. I keep pressing the C button on the keyboard to center the view. So if it's suddenly, I'll just press the C button twice. Actually, this is the origin, so if I press center view once, it centers on the origin. If I press again, it centers at the center of the mesh. So that's useful, very useful. Let's add some more nodes. How about 2, -1, and 2. Okay, and one more node, I think. So as you can see, if I highlight a node and press this node element info button, I can see where the node is and what the coordinates are. Here we have 4, 6, 2, and 2, -1, 2. So we want one around this area here. So how about 5, 5.5, 2. Oh, and there we go. Excellent. So now we have 4 nodes. It's a good start. And the thing with beam elements is if you only have I mean, I can show you. Obviously, if we want to create elements, we can do it up here with this make elements button and just type in manually the node numbers between. But with beam elements, there's a very simple way. It's this button, insert elements. There's also a keyboard shortcut. You just press the I button, and it must be 2 nodes. If you have more than 2 nodes selected, let's say for example you have 3 nodes selected, if you press this button it will create a triangular element. So a triangular element with 3 nodes, and that's a 2D element. So we can't use that in this analysis because we're making a 3D beam element mesh now. So make sure you only have two nodes selected when you insert an element. So now I click the I button on the keyboard, and there we go. So yeah, I like this. I want to, I don't know, you probably guessed already what I'm making. I was thinking we can make like a kind of a crane tower thing. Just yeah, beams. We will see. So I think I want to tilt it a little bit inwards. If you see, it's straight up here. I want to tilt this part inwards a little bit, and in order to do that I need to know the node numbers here. So we have node number 3 and node number 1, and we select the elements and click the rotate elements button. So that's node number 3 and node number 1, and let's rotate about 5 degrees. Now keep in mind these 2 node numbers, they create an axis around which you are rotating the elements. So node number 3, and the axis starts at node number 3 and ends up at node number 1. So you if you follow the if the first node number is at the base of your thumb and the second node number is at the top of your thumb, the angle you rotate is with your fingers. So it's like a right hand rule. So yeah, if that's confusing, you will figure it out. It's just try and error. So and yep. So now let's see. Can we see it? 5 degrees. Yeah. I think maybe it's a bit far away. Let's move. So every time I want to select elements or select nodes, I have to click here, select elements, select nodes. So I can't select elements now. Now I can. So yeah. Actually, I want to move the elements closer to the origin. Actually, we can do that in 2 different ways. We can because the well, actually, it doesn't matter. there's no difference here now. Now I can either move the nodes or I can move the elements. So there's one button for move elements and one for move nodes. So let's just move it a little bit closer back into towards the origin again. Yeah, I like that. And let's just double check how far it is from the origin. So yeah, that's pretty good. Now we want to split up these elements into smaller elements so that we can add more elements in between here. And there's a button that quite easily splits up your beam elements into smaller, a set of smaller elements, and that's this button up here. And now you just specify how many elements should be your original element should become. So this this applies to each selected element. So this upper one will be split up into several, and this one also. And if we say 14, we want 14 different elements in each of them now. And here you can see it's yeah, we still have the node button selected, so we can still see the nodes, which is very useful when working with beam elements. Yeah, this looks good. And now I want some elements between here. Let's see. Let's start with this and one here. I also want one here and another one here and here, I think, and finally here. Actually, I think we'll just remove these. So whenever you have elements or nodes that you don't want anymore, you want to remove them, first you select them, and then you press the delete button and delete elements selected. You can only delete selected elements. So yeah, there, and they are gone. Yeah, this I like this. It doesn't have to be like we're just making something here just to show how the program works. It doesn't have to be very realistic right now. Now I like this. I want to actually, maybe I should split up these first. I'll do that. Now I like to have consistency, as a little bit anyway. The distance between, or how long each beam element is. So here I can see, oh, it's about 0.5. It's probably about the same here. Yeah, about 0.5. So with these new long elements, let's see how far it's between. So 0.5. Maybe if I split it into 6 elements, and this one looks about the same, maybe? No, this one should be split into 5. because I have this is about 0.5. It doesn't have to be accurate, just roughly. And this is 2, so I want to split this element into 4. Oh yeah, also notice here when I select, if I hold down Control and drag select, I will unselect. So that's very useful. Similarly, I can hold down Shift and it will add select. So let's split up this one into 4 elements. And here we had, oh no, wait, no, I did not want to do that, not yet, actually. I'll delete these and add a new element here. So, okay. First, I want to copy this, and I want to mirror it about the XY plane here, and that's the mirror elements button. So you specify which plane, and you can only mirror copy about one of the origin planes. You can't select an arbitrary plane to mirror. So you have to, if you want some arbitrary mirroring, you have to move your elements first so that they are situated in a position where you can mirror them about either the XY plane, the YZ plane, or the ZY plane. So anyway, here we will mirror about the XY plane, and there we go. Excellent. Now I didn't split up this element, or well, I did, but then I deleted the split elements and added a new one because I kind of want to rotate these elements. Let's see. I want to rotate these. Oh, these, yeah. I think I want to rotate these inwards a little bit. And in order to do that, first we need the node numbers again. So we will rotate about these 2 nodes. So that's 3 and 44. So let's select the elements again and the rotate elements button. I'll rotate about 3 and 44, and let's do, oh, actually we gotta follow the right hand rule here, so it'll be the other way around actually. There we go. Yeah, this looks better. I like this better. And you know, actually it's standing very upright. Maybe it will be a little more interesting if we rotate the entire structure a little bit. Let's rotate downwards a little bit around the origin here, and then we need to select the nodes so we know the node numbers, node number 1 and node number 31. We rotate the entire structure 1, 31 and let's rotate about 15 degrees. Yeah, that's better. And now we can split up these elements. The thing is, if I had split up these and started rotating these elements, there would be nodes in between here that would not follow along with the rotation. Now the nodes are fastened to here, so when I rotate, I'm basically always rotating nodes and the elements are just following. So if I hadn't deleted these four elements that I had and created a new one, it would look horrible here. I mean, it's not a big deal. I could have just deleted them and added a new element again, but yeah. So anyway, we will let's see, there's 1.7, so we'll split this into 4 elements, I think. 1, 2, 3, 4, and we select them. We use shift select and control select to accomplish this. So let's split this up into 4. I like that. And what's the distance here now? There's the measure distance button. You just select 2 nodes and click this button and it will give you the distance between. So 2.8. Yeah, we can split this one up into 6 elements. 6. That looks good. And moving on to the next one. Here we have 2. So that's 2.5 about, and if we split these two up into 5 elements, that should be nice. There we go, excellent. And these looks pretty similar. 1.1, 1.3. How about this one? 1.1. Okay, so actually we'll sometimes you need to center the view again to make it easier to navigate. There we go. So I just pressed the C button on the keyboard to center the view. Very practical. And yeah, these, let's split them into 2 elements. And the last one, let's do 3 elements for that one. It's not, doesn't matter really, it's not a big deal. And I think we have, oh yeah, and we need, of course we need elements between these. So we use the I button on the keyboard, or this button up here, to add elements between. Excellent. And this one. And finally up here. Yeah, nice. And we are going to split up these. So let's see, we have 2, yeah, so we split that into 4. And this one into 3. No, wait. We don't need that element actually. Let's delete that one. The thing is, I'm going to lock all of these. So the boundary condition will be to just completely lock these nodes. So an element here makes no sense. What was it? 3 elements. 3 elements. And 2 elements. 2, 2, and this enough. Yeah, well, 2 there as well. Okay. So we'll do this one and this one. Split these into 3. And here, 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 and here. These we can split into 2. Alright. Yeah, this is good enough, I think. Now, from here, we need to specify properties for our elements. So, before we do that, let's select our elements. I think because I want these outer elements, I want them to be bigger, or have a bigger cross section than these smaller ones. They're obviously going to take most of the load. These cross beams are there to stabilize the structure, right? So I'm going to have 2 sets of two element sets, and so I'm going to select first these outer elements, and I'm going to include not that one, not that one. I'm going to include these as well. There. Oh, that's I did not want those. Unselect those. There. So that will be element set number 1. So element sets, we use those to apply properties, or maybe some loads also, a gravity load, for example. So element set number 1, and then we select all the other elements, all the cross beams. And let's see. There. This one. Shift and drag select. Hold down Shift while you're selecting to add, and hold down Control while you're selecting to unselect. So yeah, so that's all the crossbeam elements. We'll put them in element set number 2. Okay. Now we need a material. Our beams are made of metals, so materials here, we can create a new material, but I like to just well, see the create section button. When you click this, you create a new section, and there are some materials are already specified, so you can select between aluminum, carbon steel, stainless steel, and titanium, and also it's in well, actually, let's just create a new material just to show how it's done. Could be good to know. I don't know if I remember correctly here, but it's just it doesn't matter. We can I think 7. Oh, this could be very wrong. This will be embarrassing. But anyway, whenever you create a new material, the terminal window lists up all the materials in the that are available in your database. So here we can see carbon steel. We're working in newtons, meters, and kilograms. So how many zeros are that? 1, 2, 3. Yeah, I got that one right. About, well, almost. Yeah, it's about right. Oh, okay. Yeah, I wasn't too far off. So yeah, so now we know how to create a material, and we want to create a section. So that's the create section button, and I want carbon steel, and I'm working in newton and meters and kilograms. I could use the material I just made, but I always use these. So now we're working in beam section with beams. So you could specify here the area and the moment of area right here if you want. I'm not going to do that now because I have not calculated that. So, and there's an easier way. So we'll just create this new section with the name section 1 and this material. And actually we're going to do the same for section 2. We want two sections. So you can see down here we have 2 sections. And now we're going to modify beam section. So this if I was working not with beams, or actually it works with the truss elements also, rod elements, but not any of the 2D or 3D hex, tet, triangular, quadratic elements. This only works for rod elements and beam elements. So for this first section, I want it to be 0.2 high and 0.18. So you can see here what's going on. So it will be 0.2 meters wide and 0.2 meters high. So that's 20 centimeters. And there will be 1 centimeter between here. Yeah, I think that's right. So it doesn't matter. This just shows you how to do it. So, and when we just type in the measurements here, it automatically calculates the area and the moment of area about both axes. So that's very handy. Now obviously there are only 6 types of cross sections here, so if you want something more complicated, then you will have to do these calculations yourself and type it in when you create the section. Okay, so there we go. And for section 2 I want also a rectangle, and I want it to be twice as small, or half the size of the previous one. And yeah, there we go. Now I have 2 sections. I have 2 element sets, and actually if you click this highlight element set button, I have to move it a little bit. There you get a this is a very useful way to select all the elements in an element set. That's element set number 2. So now I'm going to apply section 1 to element set number 1 and apply section 2 to element set number 2. Okay, now notice here in the mesh tree, when I did that, now all of the elements have a section applied to it, and when all of the elements have sections applied, this changes to say applied. If you don't have sections applied to all elements in your mesh, you can't, when you try to write the solution to a file, it won't do it, because yeah, you can't run the solver anyway, so it's just like a fail check here. So anyway, now we have sections applied, and we can actually get a 3D view of what it looks like, but in order to do that, we need to apply a beam orientation to the elements. So how this works is, yeah, well, actually let's just click OK, and it will put an orientation on every element. It just defaults to that. Oh, and also the origin button hides these if they're annoying, which they are. Anyway, in order to see the cross section, this is a bit annoying, but you have to refresh. So one way to refresh is to just select elements and then hide them and then show them again. So the orientation, I mean, it looks okay, I guess. Actually, no, it doesn't. I'm going to select element set number 1 first, and I'm going to try to orient. Yeah, let's try this. See if it works. It's a bit finicky. You try and see. It looks the same actually, but it was pretty okay. What is not looking so good are these cross beams. They're they're the ones I should have. So let's highlight those and let's do that. Now I got some warning messages here. That's because I set the y-axis this way, while these are pointed in the y-axis. So the y-axis and the x-axis can't be the same inside for the beam orientation. So let's look. We have to refresh, and yeah, it looks better now there. But now when you get this warning message, it just adds a random orientation, because it couldn't set the y-axis to be the same as the x-axis of your element, if that makes sense. Anyway, we will just select them like this and unselect that one, and click the button again, and yeah, now the x-axis is the z-axis actually, and the y-axis can go straight up. Yeah, this will be this will look better. Okay, yeah, I like this. I mean, it's not perfect, but yeah, good enough. Anyway, you kind of get the you see how it works. And so now I have all my elements. I have sections applied to them with cross sections and like area, all these properties that you need to do your calculations on beams have been applied everywhere. So let's yeah, I keep clicking this shaded and wireframe buttons. So if you want to see this the cross section, you have to click the shaded button, otherwise it won't come up. But now let's move on. I want to put a boundary condition on these nodes, so I have to create a node set number 1. Okay, and I want to apply a load here on these two nodes, so that will be node set number 2. Excellent. And that is everything we need before starting our solution. So we can click the static button here, and we can write a name here if we want. Doesn't really matter now. We can use solution 1 and leave this one alone. Yeah, it doesn't matter. Just leave it be. Okay. And for our static linear static solution, we add a boundary condition on node set number 1, and we freeze all of the degrees of freedom here, all translational and rotational degrees of freedom. 0 displacement. And actually, if we press this current solution button up here, we can see a visualization of our solution. So here we can see the boundary conditions applied. And we also want a load. So uniform load, concentrated load, distributed load, torque load. So if we are just applying one load to one node, then concentrated load makes sense. We have 2 nodes in our node set, so it's much easier if we just click uniform load and apply it to node set number 2 here. This means that if we write, let's say 60,000, let's say 100,000 newtons in the negative y direction. This load will now be split up uniformly on the 2 nodes in the node set. So the total load will be 100,000. And yeah, this one, solution 1 is ready. Actually, I want to just to show you how it works. We can create an eigenmodes solution too. Here we go. We call it solution 2. And for this one, we'll just add a boundary condition on node set number 1. Make sure it's solution 2. And 0 displacement, all degrees of freedom. Okay. It's ready. We have everything we need, and we will now write sol file. So here, this will be the name of the solution file, and here we can add which solutions we want in the solution file. So we want solution 1 and we want solution 2. Now, for beam elements, you can't actually get stress or strain. You can for rod elements, but well, you can for all elements except beam elements. The program just doesn't offer this, so we just remove those. But node force and element force, these are available. And this is the number of mode shapes for the structure. So yeah, it's ready. Let's create the solution file. And you can see down here, writing sol file 1. So let's open. It will now be in the work directory, and I'm working on 2 screens here, so here we go. Here we are. I mean, it's not like very important, but we can just have a quick look. In the up here at first, it will defines the first solution here with loads and boundaries. Mesh is this is up. Yeah, it writes it in, but it doesn't need to be there. 999 is the element set for all elements in the mesh. And results, we asked for these results and the eigenmodes with the boundary mode shapes here. Material, section. Now the thing, actually, what I wanted to show you is at the end here of the section properties, these what I've highlighted here, if you remove this, you don't get the 3D rendering of the cross section. You just get the wireframe of the beam element. And so just yeah, now you know that. And yeah, this looks kind of horrible. These are the beam orientations that were applied, and down here these are the boundaries we made for each solution, the force and the node sets and element sets. Now this is really this mess is because of the beam orientation, but you know, it is what it is. And the nodes and the elements. So yeah, that's what the solution file looks like. And yeah, the solution file is here. So now we can run this solution file from the solver here with this button. We select the solution file we made and run that. Now here you can see it went very quickly because they're just beam elements. So it ran 2 solutions, total mass, yeah, 576 degrees of freedom. So just it shows the solution running through here, and it made now 2 files, one result file and one out file. So we didn't really ask for any results in text format, so this, I mean, there will be some there will be something in there. We can have a look what it looks like. So it's much of the same as here, but actually, yeah, it does show the reaction forces on the nodes, and as we can see here, 100,000. So it adds up with the load we applied, and we did not apply any load in the X or Z direction, so they are basically 0. And we also have a reaction moment in the RZ rotation, which makes sense. No moment on these directions. So yeah, actually, yeah, this for the eigenmode solution, it does give you some information, which is probably useful when you having like a reality check. So inertia tensor, yeah, and center of mass, that looks about right. Yeah, should be right. And here the eigenfrequencies are listed. Now, of course, these are the modal effective masses. They can be really useful, but they're wrong here. So ignore these modal effective masses. Eigenfrequencies are here. They are useful. to know. So now let's open the solfile1 out file. This is not a text file, this is a binary file. Python lets you save data as with a module called pickle. So you're creating a binary file that holds the data, and you can open it. It saves Python variables, so as binary. So well, actually, I might be wrong when I say binary. It might, but anyway, it lets you save Python variables in a format that is easy to load back into your program. So we can see here we opened solution file 1 out file. Yeah. So and it loaded new results. Solution 1 displacement, node force, element force, and solution 2 mode shapes. So let's start by looking at solution 1. We can have a look at the displacements, and it looks really chunky. Might be a bit, I don't know, maybe we want to lift very heavy things. You can see here the displacement is so is that like 2 millimeters? That's very little displacement anyways for 100,000 newtons. So we built a strong structure here, there's no doubt about that. But anyway, it's moving, we assume at least, it's moving down in this direction. We can, we can, if you look down here, you see the current deformation scale factor is 20. So let's ramp that up to 2000. And yeah, here we see a little easier which way it is being deformed. Yeah, that makes sense. Just bring that back to, well, actually let's put it at 200. Maybe that looks, yeah, easier to see the deformation there. So these are the displacements. Of course, if you want, we can have a look at the y displacement, or displacement in the y direction. And here we see 1.5 millimeters downwards. Also, if you if you click the wireframe button, you remove the rendering of the beams here. Oh yeah, actually, so you can see here the node coordinates. If you want to select nodes or elements, you will want to put the scale factor to 1 actually, which will make it easier to select them. And if you want to know exactly the displacements at this node, because now we are in displacement results, you can click the node element info button up here, and the terminal window will print out the displacements for you here. So node number 4, displacements in x, y, z, 3 rotational and magnitude. So x, y, so 1.58 millimeters in the negative y direction. Yeah, okay, that's enough displacements, I think. Let's move on to node force. So these are the external forces, or the forces on the individual nodes. So we applied. It's like it's useful for a reality check. So we applied 100,000 newtons here, divided on these two. So here you can let's use this node element info button again, and here you will see, yeah, minus 50,000 newtons in the negative y direction. And of course it will be the same on the other one there. Yep. You can also, of course, you can see here, like, yeah, 50,000, yeah. And the reaction forces, you can, let's see, down here we have 68,000 in the x direction and 110,000 in the y direction. Also a little bit in the z direction, and also some moment here. This one, yeah. So you can go in and probe values as you want, but it looks, yeah, this makes sense. It's pulling down here, it's pushing back up here, and it's holding back up here. So yeah. We can also visualize the moments, because we locked all degrees of freedom here, so it's being held back with a moment here, and the same here. Yeah, so this makes sense. Yeah, looks good. And you can see the how big of a moment this is. And finally we have element forces. So Fx, element force, this is the axial force in each element. And here we can see it's red and orange up here, so this is in tension. So the red, orange elements here, they are being stretched, and down here is in tension, so they are being compressed. You can see the values here. So this makes sense. And these stabilizers here in the middle, they look pretty much like they will be 0. We can probe the values like we did for the nodes, and then we see element forces here. So very little, I mean, they're a little bit in compression there, but yeah, they're pretty much just holding, stabilizing the structure, which makes sense. These look a little bit more yellow, actually. So maybe they are being stretched. We can have a look. They are being stretched, yeah. And these then are probably being compressed a little bit, yeah. So this makes sense. That's what we would expect. And we can also look at shear forces. Now these are shear force diagrams, so you probably made these by hand, and it actually they look a little bit big here, so we'll just we can use this scale diagram button. It's set to 1 by default, so let's set it to 0.5. And yeah, shear forces, I mean, makes sense that there would be more shear forces up here. Yeah, looks reasonable. And in the Z direction, also this makes sense. Yeah, the forces are pushing and pulling, or yeah, there are more forces in the shear direction here. Makes sense. We can also look at the bending and torsional. So this is torsional forces, and they're fairly low, I think. Looks like all of the elements are being torqued or twisted a little bit inwards, I guess. Yeah. Well, anyway, you get the picture. If you want this information, then it's available. Actually, for at any whenever you're looking at element forces, you can select an element and again node element info, and then you will get all of these forces listed up. So that's node 1 and node 2, and the forces at the nodes. If you need, maybe you need to calculate the stresses, or yeah, now you know where to find the forces. My and mz, of course, these are bending moment diagrams. So this looks, yeah, they're being bent in this direction. Makes sense. And these are fairly high actually compared to, I bet these will be much lower. Yes. So again, it makes sense. Yeah. That's all of the results for solution 1. Now we also created a solution for eigenmodes, so we can look at that now actually. And 10.56 hertz. It's swinging from side to side. Yeah, well, that's good to know if you have dynamic loads. And when we want to select the next mode, we can either do it here, mode 2, and it's a bit slow in loading because it's rendering all of these cross sections. So there's a lot of rotation going on. So it takes more time to load than you would think. We can move, actually when we're looking at eigenmodes, we can stop the animation, start the animation again. We can set the speed here, and we can switch between the nodes, eigenmodes. When we click the next mode, if that mode has not been loaded yet, it will be fairly slow, so you will see the program freeze for a second here, and it doesn't show the loading graphic when you do it. When you do it this way, it will show the loading graphic, but when you do it this way, it does not. So just keep that in mind if you have a very big model. Yeah. So actually, I think, yeah. So when an eigenmode has been loaded into the viewer, you have already looked at the results. It just pops up right away because then it's been loaded into. So the reason why it works like this is because otherwise you would have to load everything when you open the file, and then that could take a very long time if you have a big model. So it's just practical this way. So mode 1, swinging from side to side, have a twisting here. That's 33 hertz, so that's pretty stiff. 34, another one of these twisting modes. And here we have up and down, yeah, 36. And another one, twisting. And well, this one is, yeah. We only did 8 eigenmodes, I think. But anyway, it's that's how the eigenmodes solver works. So I think that does it for this second tutorial. I hope you found it useful, and now you can create your own beam element mesh and apply loads and run solutions. Check out the results. So thank you for watching, and have fun.